few more definitions, a little bit of terminology here, just so that we get the lingo and so we understand the relationships. Remember, it's the relationships that are key here. So we classify inventory, and for us, into two big categories, one of which is cycle inventory, the other is safety stock inventory. Cycle inventory is the amount of that inventory that varies directly with lot size. Lot size is just a way of saying order size. Okay, and that lot size varies with how long between orders, right? Of course, longer time between orders, we need to make bigger orders. Shorter time between orders, we order smaller orders, right? It kind of makes sense. We're keeping demand sort of constant throughout this whole analysis. Okay, so if a lot is ordered every week, you need to have at least a week's worth of demand that you're ordering. Order every month, you need to be ordering at least a month's worth of demand, and so on. Right? And it kind of makes sense, right? And the longer the time between orders, the greater this cycle inventory, or Q, needs to be. That's flows. I think that's fairly intuitive. Okay. So we're going to imagine what we're working towards here is how much is the average cycle inventory, because we need that for our calculations. So at the beginning of the inventory, cycle inventory is at its maximum. It's size Q. Whole order comes in. We haven't sold anything yet. All right, so we start at Q. Throughout the term, throughout the days, throughout the minutes, throughout the seconds, throughout the week, whatever, we sell, right? We're selling stuff. And so obviously our inventory is drifting below Q. And at the end of that inventory period, when the new order is expected to come or be there, we've sold everything. Let's assume there's a whole bunch of assumptions in this, but we've sold everything. That's kind of like the general theoretical approach here. Okay, so we look at and we assume a distribution. Basically, we're assuming this sort of that the sales are uniform throughout the period. You know, we sell a same amount every day, same amount every week, or what have you. And so that the average between Q, which is our max, and 0, which is our min, is Q plus 0 divided by 2, or Q over 2. Right? That's our average, the middle amount. Right? And based on an assumption that we sell uniformly throughout the period, or uniformly between orders. Okay, so we have that. And so we have this idea of a cycle inventory, Q over 2. We also have an inventory called safety stock inventory. And safety stock inventory is there to protect us against uncertainties, variability in demand, lead time, and supply changes. Okay, so what happens? Well, you need that special inventory because sometimes suppliers fail to deliver what they promised or what you expected, or they failed to deliver it properly. Look at masks here, right? Vaccines and all that kind of stuff. Right? You think about it in the very high-profile sense. Right? Or they failed to deliver it within a certain period of time. Lead time is highly variable. Right? You're expected to get this stuff in a week. Turns out now you're getting stuff in 2 weeks. Well, you got to adjust your inventory for that. Or sometimes it's 1 week, sometimes it's 4 days, sometimes it's 10 days. I mean, there's a huge amount of variability in that lead time, and you have to make adjustments for it. Right? So safety stock is there to protect you against uncertainties. So it's like an insurance. It's like buying ourselves a little bit of insurance. And so uncertainties in demand, uncertainties in lead time, uncertainties in any supply changes because variability in our supply chain. Our vendors or our suppliers are just unable to supply what we expected that they would be able to supply, or what they promised to supply, or that kind of thing. Okay, so all those uncertainties, we have safety stock to help us protect against that. Now, inventory reduction cat. Now, we're starting to get into the policy, and this is very important stuff here. Not so much for the mathematics. The mathematics show us the relationship, but we're concerned about the relationships. So, when we start talking about cycle inventory, we start talking about order sizes. Now, when we reduce those order sizes, that means we have to order more often. Well, there's a cost to that. We have to change over our production processes more often. There's a cost to that, right? If we're changing what our bottleneck resource, our key machine is producing, we do that frequently, increases the downtime for that machine. We saw that in the movie The Goal. So important issues here. We have ways that we can deal with it, and auto companies are really good at this, is they have changeable pieces. But issue to consider. Not a big one for us, though. I mean, it's a big issue, just not one that's a focus in our course. Safety stock is we're trying to meet variabilities, for instance, in demand, dealing with supply and delivery uncertainties, and we want to keep meeting that demand, right? If there's a sudden improvement or a sudden increase in customer demand, we want to be able to make those sales. We don't want to lose out on those sales. And so in order for us to deal with any kind of variabilities in customer demand, we have a little bit of extra safety stock inventory available so that we can meet that demand. Very important. Okay. Other ways that we can reduce that, or ways that we can reduce that safety stock, is if the lead time shortens, right? If there's smaller lead times, we need less safety stock, because during one day, less crazy things will happen than less will happen during one day than will happen over, let's say, 1 week, where the scope or the probability of something unforeseen or odd happening during a week is higher than happening in the next 5 minutes, just to take one extreme example. Right? So we could kind of see that. Lower those lead times reduces the scope for demand uncertainty, because if demand all of a sudden goes up and we have short lead times, we can place an order really quickly, get it in, and deal with that sudden demand very quickly. But if there's very long lead times, or those lead times are long, that's harder for us to do. Okay. Supply uncertainties, so that we have safety stock because our supply chain is a little bit tumultuous, or there's some uncertainties there. Anything that we can do that reduces those uncertainties, right, so that we get what we expected, we reduce variability in that sense, then that is a really great tactic for reducing safety stock inventory. Now, the economic order quantity. Now, the economic quantity theoretically is the order size or lot size, a Q. So Q is just an order size. EOQ is the economic order quantity, and that's just the order that minimizes total annual inventory holding and ordering costs. Stress the word annual, okay? Because sometimes the data you get, the info you get, is not in annual amounts. Then it's not in yearly amounts. It could be monthly amounts. It could be weekly amounts. It's whatever is easily available. So we need to keep track of our time units quite carefully here. Now, we start off with a few assumptions. Some of them are a little bit goofy, and some of them aren't a big deal. So we start off with demand rate is constant and is known with certainty, which we will relax in the future. But we start off with that just so we can we're isolating the relationship. The key is the relationship, not so much, there's a little problem here. They wouldn't really use economic order quantity to make an order. And yes, that's true. I know it. People know it. Yes, that's true. But the relationships that go into determining the cost minimizing order size, those are solid. Okay, so relationships are what we are most importantly focused in on. A formula or an equation is just a very tight, abbreviated expression of a multifaceted relationship. Rather than spending 2 pages discussing a relationship, one formula sums all that up. So it's very abbreviated, very compact, very efficient that way. No constraints are placed on the size of each lot. That one can be a little bit goofy depending on what you're ordering. The only two relevant costs are inventory holding costs and the fixed costs. That we can deal with. We can pretty much squeeze and manipulate, sort of put everything into one of those two categories. That one's not too bad. Decisions for one item can be made independently of the decisions for other items, so there's no bundling. If you buy this, you get that. Some cases bundling, some jurisdictions bundling is illegal, so that's an assumption. It's pretty law enforced, but we're going to assume that it's not an issue outside of law enforcement. Lead time is constant and known with certainty. You can make adjustments where that's the case, but nevertheless, even if you have the relationship where the lead time stays constant and is known for certainty, we are still able to discuss how a changing lead time can impact our order size or our economic order size. Okay, so it doesn't prohibit us from having the discussion, just kind of impedes us from coming up with a single number calculation. But that's not a big hindrance at our level, given that we're not getting too deep into the weeds of inventory management. EOQ doesn't work so well when you have a make-to-order, customized. You're making stuff for a customer, or the order size is constrained. Then, of course, you have to make adjustments. You can modify it for quantity discounts. You just make little formulaic adjustments. These are not that hard, and in many cases, software can deal with that. Replenishment is not instantaneous, so hey, there is a lead time. You can adjust for that as well. EOQ is nicely suited for make-to-stock, so you make it for inventory like we did with the LaBolt, and then you sell out of inventory. And of course, it's very important that the carrying and setup costs are known and somewhat stable. That's kind of an important one there, the stable. We can analyze what would happen if there were changes, but it gets a little trickier if we try to analyze what happens when costs change at the same time that lead time is changing. That could get to be really complicated. So essentially, here's sort of our world. We start off at Q, we sell, and then we reach zero, and boom! It's kind of a highly theoretical, stylized world. We sell that last item, we put in the order, and instantaneously our order is received. And for some things, this can be so like electronic items, like information, can happen this quickly. We receive the order, and then we go through the same cycle. And that's where we can get an average cycle inventory of Q over 2. Okay. So, yes, a highly stylized world for sure. Okay. Well, we can shift this around, and we can tweak it a little bit to deal with different situations. But this is sort of how our starter system, if you will, and then we'll make it more complicated as this little unit goes on. So we have our annual holding costs, our annual ordering costs, and together they form our annual cycle inventory cost. And annual ordering cost is just the average cycle inventory, that's at Q over 2, times by the unit holding cost. How much does it cost us to hold one unit for 1 year? Remember, these are all annual numbers. Okay. Ordering cost is the number of orders you place per year. Again, keeping with our annual theme, times how much it costs to put in an order or to do a setup. That makes sense, right? How much does it cost for every time you make an order times the number of orders you place in a year? Gives us your annual ordering costs in a year. We add those together, and we get our total annual cycle inventory costs, or total costs. Now, that's our starting point, right? And we're going to take those costs and we're going to try to minimize them. We want to minimize those total costs, right? So we're trying to get on the curve on the lowest part possible. And that happens to occur roughly where, or actually theoretically occurs exactly where, holding cost equals ordering cost. So we're at the intersection of those two curves is the minimum value for total cost. And if you're taking used to be in the old days, Never know when Econ 281 changes, but in Econ 281, when you're talking about cost minimization, it's usually holding cost is like our variable cost, and ordering cost is like our fixed cost. Ordering cost is kind of fixed, right? It doesn't change per order. Holding cost does change by how much inventory you have, right? Size of the order. So you can kind of think of holding costs as that variable cost, ordering cost is that fixed costs, and where the two intersect is where your total cost will be. Now, a couple of observations here to keep in mind is total cost is pretty flat-ish at its minimizing point, which means, EOQ a little higher, EOQ a little lower, that's okay, right? And so if there's a minimum order size, we have to order a little bit more, it's probably still going to be the cost minimizing point because there's a certain flatness there. So whether it's a couple items more, a couple items less, not really a big deal from an EOQ point of view. Nevertheless, the order quantities come in integer amounts. You do not order a part of a calculator. You order the calculator. You order a certain amount of cell phones. You don't order 4 cell phones plus a half cell phone. Okay? So we kind of keep common sense still in our heads a little bit. And it's easy to lose common sense when you get lost in a pressure situation and you're doing calculations. So we have our annual cycle inventory cost, and we see the cost is equal to Q over 2, which is the annual cycle inventory, times by H. Now, units are extremely important here. H is a holding cost per unit per year. And then the number of orders that you place, and we calculate the number of orders that you place by taking how much you sell over a year divided by how much each order size is. Now here we're assuming that we're not holding, we're not doing anything. We're matching demand. Demand is somewhat constant at this moment. Okay, so we know how much we're going to sell. We looking at our order size and how much we sell divided by how much each order size is represents how much orders we placed. Sort of the reverse of this, right? See, number of orders per year times by the ordering or setup costs. That D over Q is just the number of orders per year times by the setup or ordering costs. And there's our total cycle inventory. Haven't incorporated safety stock into this, but we easily can. Now, what happens now is we want to minimize the cost, and here what we do is we basically take the derivative of this equation with respect to Q, and then we set it to 0, which is how you would solve the cost minimizing point from a calculus point of view. Okay, we do that. Now we don't have to use calculus, but when we do that, we get the EOQ, which is just a Q equals to the square root of 2 times the annual demand times by the ordering cost divided by the holding cost per unit per year. And together that forms the EOQ. Once it becomes the once it becomes the cost minimizing order quantity, or once it becomes the cost minimizing Q, that Q changes to EOQ. But EOQ is a Q. It is a order size. It's just a special type of order size called the cost minimizing order size. And related to that EOQ is the time between orders. And if you take the economic order quantity divided by D, that tells us how long between orders. And that's an important relationship as well. Okay. Now, because everything was in annual numbers, demand is annual, that's a time between orders in years. And that's important to realize. And that time between order in years is, we have to convert it if we want time between order in days or weeks or months or what have you. Okay, we got to be able to do the conversions. You got 0.207 years. Nobody talks like that. They want to know how many months is that, how many weeks is that, how many days is that. Okay, so we may do the calculation using formulas, but we still want to talk human. Okay, still want to talk in terms that people can understand. Okay. And last thing is the managerial insights, which is the most important part. Because again, I admit EOQ is a little bit theoretical. It's not really used in the way that it sometimes is implied in textbooks. That's true. Guilty. I'm not going to lie to you about that. But the relationships are important. So if demand goes up, all right, we look at the formula and go, hey, there's been a demand. We are forecasting. The forecasting folks have determined that demand is going to go up next year or go down next year. What is that? What's their impact on our order size? Well, I'll look at my EOQ formula and it says, okay, well, we're going to be looking at increasing those order sizes. Okay? So we're going to be now having to go through the process of starting to negotiate order sizes that are larger. Hey, maybe we can qualify for quantity discounts. The whole supply chain process now kicks into gear, right? So if the demand is expected to go up or is there forecast to go up, we're going to need to increase those order sizes. And we can kind of see that just looking at the formula. What if we're able to reduce the order costs? Well, we bringing in a new system allows us to reduce how much time it takes to determine the order, to place the order, or to send the order. What if we could reduce those costs? I look at the formula and go, hey, we could probably get away with maybe reducing that order size. If those costs all of a sudden go up, we may be having to look at increasing the order size, right? So we can really see the implications. Holding costs. Now, when we think of ordering setting costs, right, at the very beginning in the last part, we talked about all the elements that go into an order or setup. Right? So any of those elements go up, S is changing. Or any of the, maybe I should better say, if any of those items within the order and setup costs category change, S changes. And when S changes, EOQ changes. And we need to follow it through. Same thing with the element of holding cost. You're not going to get a situation where somebody goes to you, well, H has just gone up or H has just gone down. What's that effect on EOQ? No, nobody's going to tell you that. It's going to say, okay, it looks like there's an increase in interest rates. Well, what's an increase in interest rate? What's that going to do to our order size? And you're going to use the formula to figure it out. Right? Increase in interest rates, that means an increase in holding costs. It's going to be a decrease in order size. Right? We can follow that through in the formula. Right? Hey, inventory warehouse space. It looks like it's gone down. Bunch of supplies come on the market. Prices dropped. How does that impact our order size? Well, in that case, H is going down. H is going down. The denominator is going down. It means the overall number is going to increase, which means we're going to be able to place bigger orders. Okay, so that is the key deliverable. Knowing how to do the grunt calculations. Yes, there'll be easy peasy little questions on a midterm that do that, and that's cool. It makes sure that there's always questions that everybody can answer. But the more important questions are, can we use these relationships in these formulas in order to discuss and be able to explain the policy implications that these represent, right? That's our true management deliverable here. Okay. All right. Next unit, start talking about those inventory control systems. First the Q system, then the P system. Stay tuned.